Let's get started. So you remember, we load the data, we drop the null values and so forth. Remember, the pandas profiling is a great tool to quickly get descriptive statistics, a preliminary descriptive statistics. It is not everything. Don't always completely rely on this. This was the flag data set. We got the descriptive statistics on it. And then it gives you quite a bit. Then remember, the first thing we do is we extract, we separate. If you're doing supervised learning, either classifier or regressor, the first thing you have to do is extract out the target variable from the data. And now you have a separation between the feature set, the features that feed into, or the independent variables, and the dependent variables. Another way to say is input and response. Capital X by convention is the input, capital and little y is the response. Why is that? Because X would be a matrix, because there are many features producing the input, and a row is like there are many rows, so it's a matrix, whereas Y is a column vector. Matrices are capital in general convention people follow, and Y, they write it as a column vector. Actually, I take that back. In neural networks, all those conventions go out of the window because everything is matrices. All right, so we visualize this data. If you remember, this was the visualization of the data. Right? And just to remind you, this was a theory of logistic regression. Basically, what we said is log odds is the distance from the decision boundary. By the way, I have a video on our website, on our YouTube channel, about distance from the decision boundary. You might want to consider watching that. It is quite relevant in the context of, let me show that to you. It's a very short video for 15 minutes. Why do I call it distance from the decision boundary? It is because youtube.com/support vectors. If you go down here, you see linear classifiers, distance from the decision boundary. This is the video I'm referring to. And you will realize that at the end of it, let me go straight to the end. Yeah, you will come to the conclusion, as you do here, that this equation, or this beta naught, etc., here W, it represents a distance from the decision boundary. In other words, this thing is the distance from the decision boundary. All right, so that's a little bit of theory for those of you who remember your ML100. We'll build a model. If we try to naively build a logistic regression model, as we realize, it's a disaster. It's a baseline model. It just degenerates to the baseline model where the majority class is the predicted class, or the 0R model. Next, we try it with polynomial regression, polynomial logistic regression. We expanded the feature space with polynomial terms. When we expand the feature space with polynomial terms, we get a pretty complicated model. You see how complicated this model is. Right? And the fifth degree polynomial. But then if you try to look at how good this model is, still the accuracy is only about 69% for the 0, which is the real positive test case here. There are fewer zeros here, 85 for 1, but it doesn't. So then we do a more careful analysis by extracting the river, modeling the river with the line. Oh, where's the line gone for the river? Okay, I seems to have not run the visualization. Look at the model diagnostics. Model diagnostic looked good. These were the model diagnostic. You remember we talked about having a homoscedasticity in the residuals, and the residuals must show a bell curve distribution, which you see on the side. All of those are good things. A good correlation, positive correlation between prediction and reality, which again is here, the Cook's distance, to show if any points have high influence. None of them seem to have, they're all doing well. And finally, here it is. We visualize the model over the data. So we now have captured the river, the center of the river. And so it helps us extract the feature, namely just the distance from the center of the river. And we are done. After that, we just have to build a logistic regression in one variable. Just look at this. We are using a feature space of just one variable. We ignore all the input variables and we are just using D, which is a new variable, the feature that we extracted. And when we do that, we get a model that is actually already from the confusion matrix begins to look good. And when we do the classification report, we suddenly see that it has very good accuracy, 84% for the 0th class, generally. Overall precision, the harmonic mean of these two is pretty good. Accuracy is 89%. So 89% accuracy is a pretty impressive accuracy. Even for the positive test case, we get 84%, pretty good accuracy. We can see how the precision and recall is for each of the two classes. For the 0 positive class is this 85, 82, 83, and so on and so forth. Pretty good. The ROC curve, again, if you remember what matters is the area under the ROC curve. When we look at the ROC curve, the area under the ROC curve, it's an impressive 96% of area under the ROC curve. Pretty good. How often do we get mixed up? So for blue, we misclassified some blues as yellows, the sand, and some ones we misclassified. Very few number of ones we misclassified as 0. So this is it. So now the question is, we learned about decision trees, isn't it? The theory of decision trees, just to recapitulate, we learned that a decision tree goes about recursively splitting the region. It uses either Gini or entropy as its impurity index or disorder measure. And then it uses information gain as a criteria to split, where to split. Okay? I hope this time you all understood information gain. That reminds me, I have to send you a survey, guys. Do please attend that, respond to that survey. Like you notice, if you feel you didn't understand something, I always repeat it. Right? So that's how I discover if you did. So now that theory, when it comes to practice, what does it become? It is a pleasant experience. It becomes just 3 lines of code. One line to, this is just importing the library. This is to build the classifier. Do you notice that you build a decision tree and you fit it to data, training data. You make predictions, you get predictions, and then what do? We look at how good those predictions are. We look at the confusion matrix. The confusion matrix looks pretty good, right? The principal diagonal has most of the elements, and off diagonal doesn't seem to have that many elements, which is very good. If we do a classification report, you see an accuracy of 87%. Not quite as good as our feature engineering, but still respectable. Right? So this model is not really as good as the previous, doing it carefully by hand, but still it's a respectable measure. Now, when I build this decision tree, one of the things I didn't specify here is how deep was the tree. So we can specify actually those parameters. So there are a lot of parameters that we can use to tune the tree, and perhaps it will make it a little better. Then once we do that, we can create, as you notice, where am I? Decision tree on the river dataset, right? So this is it, overall accuracy of 87%, very good accuracy. And then, so it just shows how these nonlinear methods or decision trees are quite effective. And you see the reason why when decision trees came onto the scene, people, they really went overboard with it. You know, there were exaggerated statements that this is all you need to do in machine learning and so forth. Those times have changed, of course. Today, decision tree is not considered the state of the art by any means, but it is there nonetheless. So, yeah, go ahead.
Yellow brick classifier, any reason to use that?
Yellow brick classifier? It is a library that helps you visualize models.
Okay.
Model diagnostics. It helps you visualize model diagnostics. So here we go. We look at this. So guys, look at this. Decision tree produces a ROC curve like this. For a moment, just stare at it and tell me, is this better or worse than what we did in feature engineering compared to this. What do you think, guys? Are feature engineering ROC curves were better, or the decision tree ROC curve is better?
Feature engineering one is better.
Yeah, it's much superior, right? And it also shows, guys, that if you can do feature engineering, it is the gold standard.
Yeah.
Machines will only try to achieve that, right? But not always be successful. Sometimes they are successful, so quite often not, but it comes close. When you try to visualize this decision tree, remember the whole value proposition of decision trees is that they're interpretable. I'll let you decide how interpretable this picture is. How many of you feel this is a highly interpretable picture? I'll open it in a new tab. Where is it? Yeah, and I'll expand it. Even in its expanded form, how many of you are delighted that this looks like a very simple explanation of that river dataset? You wouldn't feel that, isn't it? It's a very complex explanation. It is almost a black box, though in principle, decision trees are highly interpretable. In practice, the moment you give it a non-trivial dataset, you begin to say you see all interpretability going out of the window pretty soon. Whereas a feature engineering, it was so easy for us to interpret. We had an intuitive explanation. We said distance from the center of the river. And that is the difference. This is why good feature engineering is the gold standard. We will do this now again with random forest. When you do it with random forest, once again, we studied the theory of random forest. You use a lot of trees and so on and so forth. You see me do that. We'll grow a lot of trees. How many trees will we grow? We'll grow a forest of 1,000 trees. When we grow a forest of 1,000 trees, and by the way, number of jobs in parallel, this is the degree of parallelization, how parallel you make it. So the more parallel you make it, the better. So for example, if I say number of jobs that will run in parallel is 100, right? Obviously, if your machine has that computing resource, then by all means, you go and do it. And if you do that, notice that this random forest built on my machine in 1.6 seconds. But don't expect the same on your machine. If you have a Gorilla machine, it may finish even faster. If you are running it on a laptop, expect it to run for a minute or so. Right? Let it run.
Is that a standard for 1,000 trees, or how did you pick that?
Yeah, that's a very good question. How did I pick 1,000? See, my basic rule is I never take more than 400 trees or 500 trees. Now, the other rule I use, I count the number of predictors. Here, the number of predictors were 11, right? Oh, no, sorry, not 11. Here's the number of predictors is 2, right?
Number of predictors are 2,
right.
Okay.
I multiply 400 by number of predictors.
Excellent. Okay.
So it's see, we live in the computational plenty.
Yeah.
So we can sort of go overboard. There's nothing wrong in going overboard. So 200 times to 400 times 2 is 800. So I approximated it to 1,000. Right? It quickly ran through. But do we really need 1,000 trees? Probably not. Maybe I could have gotten away with 400. I usually don't go below 400.
Okay.
The default is 100. And the reason the scikit-learn and all these things have a modest default is because they're trying to make sure that the code runs, the library runs on people's laptops. And some laptops will be pretty underpowered. Right? So that's that. So
sorry,
now,
what did you mean by number of predictors is 2? Sorry, I didn't get that.
The river data set, what is the dimensionality of the feature set? X1 and X2.
Oh, okay.
That's
two variables. Okay.
So that is that. So now that is all I'm talking about here in the random forest. And so you run it. This is the level of parallelization. That depends upon how good a machine you have. So model diagnostics is again simple. The same model diagnostics that we have been doing. So do you notice that, guys, certain things become boilerplate? In every analysis, you'll do that. Once you build a model, if it is a classifier, you'll need your confusion matrix, you'll need a classification report, and you will do the ROC curve, right? So once you practice this, you will use it for the rest of your life. That is the value of it. While this is good to do, I must also say that when you interview people and you see people from different programming houses or different data science houses come to interview with you, most often you find that people are sloppy. They don't actually do the model diagnostics carefully. Right? So you have to just learn to do it right once and then do it. All right, so with random forest, you see that the ROC curve, is it looking better than the decision tree, guys?
Yes.
Yeah. So can you guess why is this better than the decision tree? What is wrong with decision trees?
There is a limit to the what to say, extent, or that the branches of the tree, we are limiting it.
No, actually the problem with decision tree is exactly the opposite. It tends to just go and overfit to the data. Remember, it fits the data hard, right? And so you have variance errors. But a random forest, because it's an ensemble of lots of trees, it reduces your overfitting problem, right? Because it's a voting machine. Different trees are built or looking at different aspects of the data. It is very hard to overfit because each tree gets to see only a small window of reality. So even if it overfits, it will overfit to a very small window of reality, never to the whole reality. Right? So random forests, therefore, are much more robust against overfitting. And it gives you a clue that the reason the decision tree failed is because it was an overfitting problem. And that showed up, right? Look at the tree it built. When you look at a tree this complicated, what do you conclude from this very, very complicated tree, which is practically impossible to read? What you conclude is that it has gone and overfit to the data.
Yes.
Right? That is it. See, complexity, unnecessary complexity. We are able to explain this data in one line, distance from the center of the river. But this decision tree needs such a complicated explanation to explain it. Right? So that's a classic illustration of overfitting. Then random forest certainly seems to do better. But even if you look carefully, you notice that the ROC curve of this is only 95%. Remember, hand created your feature engineering gave you 96%. So random forest does come close and you can tune it and try to tune it and so on and so forth, right? So now what you can do is you can try to take one tree from the random forest, right? I just took the first tree from the random forest and said, show me how does it look? And you realize that each of the trees still looks pretty complicated, isn't it, guys? But because you are doing an ensemble over all these different trees, your answers are better. Now, one of the things that you get in decision trees and random forest is an overall very rough measure of how much did each of the features matter in helping you decide about, make a decision whether something is river or not, is a river point or not. It is called feature importance. How important is some feature? Just to give you an intuition, let's say that you're selling ice cream on a beach, right? Then temperature is an important feature, wind is an important feature, day of the week is an important feature. But suppose in the data, somebody has given you the number of penguins in Antarctica who jumped into the sea that day. Just because you have that as a column or as a feature in your data, it doesn't mean that it's a very relevant feature. So in feature importance, its importance would be close to 0, and the more significant features would trump. For example, temperature would trump, and so on and so forth, right? So that's about feature importance. In the same way, if you talk about classifier, we are talking about deciding whether something is a cow or duck. You would all agree that size would be a pretty important factor, isn't it? Yeah. But when you're looking at the cow or the duck, right? Take something fairly irrelevant. Let's just say that if they have stripes on their body or some sort of a straights or color lines on their body, Whether the color lines are horizontal and vertical, perhaps doesn't matter. Or you can take of some other irrelevant feature, like how much mud is there on their feet, as far as you can make out. Probably may not matter because both of them may or may not go through mud, right? So that is the value of feature importance in determining the answer in predictive models. Now, one of the things I gave you guys is a flag data set. And I gave you a hint that flag is just a small twist on the river data set. So how many of you solved the flag data set?
I did.
Yeah, there is you did. And anyone else who did? You did. So I'll walk you through actually. It was just a small puzzle. See, when you look at the flag data set, you visualize and it looks like this. Does it look remarkably similar to the river data set, guys?
Yes.
Yeah, it looks very much like the river data set. So now what do I need to do? Except that if you're if you're on the one side of the river, you are this greenish color. If you're on the other side, you are the yellow color, isn't it? So when we compute the distance from the center of the river, the rest of the feature extraction is exactly the same. But the only difference is, do you notice that you don't take the absolute value? This is the only one line change. In the river, this one was absolute. Here, it is just as it is. Distance from the center, positive distance will make it green line, negative distance will make it yellow line. That's all. And when you do that, you again do your analysis, exactly the same analysis, the same feature building of logistic regression. You notice, except that now it's a tri-valued thing, and here is your confusion matrix. Looks pretty good, I would say. The principal diagonal is heavy in red. The off diagonals are pretty light, right? And the number of mistakes you are making are very, very low. And if you look at that classification report, you have a close to 89% accuracy, fairly impressive accuracy. Right. So with feature engineering, this is it. Once you develop the art of feature engineering, right, you can use the intuition you develop in one data set quite often into other data sets. Right? Obviously, here I engineered it to be such that you could use the intuition from one to the other. Let's look at the ROC curve. Would you guys agree that the ROC curve here is pretty good?
Yes.
Right. In fact, it is 94%, 98%, and 99% ROC. I would consider those pretty impressive ROCs here. And then this is the beauty of feature engineering by hand. I mean, when you feature engineer, very rarely do more black box algorithms come as close to it. But here we go. It depends on the context also. Sometimes it's hard. The reason you use black box algorithms is you can't feature engineer. You don't have the intuition. You can't visualize it, right? So you let them do the feature engineering for you. So here we go. The number of mistakes, how often the river points are sometimes confused as green, sometimes as red, right? And so on and so forth, 1 and 2. There's a little bit of a mistake here, a little bit of a mistake here. Now, suppose I try the decision tree classifier on flag. The code remains exactly the same, no change, except that I'm feeding in the river data set here. When you look at this, what is our confusion matrix is here, looks pretty good. You give the accuracy. Do you know that the accuracy is only 86%, guys? It is significantly less than your hand engineered feature engineering exercise, isn't it? And when you do the classification, that's your classification report, and this is the visualization of it. Once again, when you look at the decision boundary, I mean the ROC curve, you're 85%, 91, 93, good, but nowhere close to the 98 and 99% kind of numbers you were seeing with feature engineering. These are the number of mistakes, right? And I'll leave the last part, doing it with random forest, as an exercise for you guys. From here onwards, do you think you can complete the rest of the exercise, guys? Doing it with random forest?
Yes.
Yeah.
Straightforward, right? So fill in the gaps. I've deliberately left some things unfinished. I'm posting the solution to Slack, right? And obviously, please don't post it on the public web. This is otherwise, I wouldn't be able to teach the next class. They would say already all the solutions are there. They wouldn't even try. They'll just take the solution and just say, oh, I'm done. Shouldn't be like that. So, all right, this is it. Now, any questions, guys? I sort of went through this. This is the way, ideally, you should create your notebooks. Right? So, by the way, Dennis, what method did you use to find? Was your method for the flag what I used, or was it some different method?
Oh, actually send you the R code on Slack.
Yeah. No, but could you explain what approach you used? Was it the same or slightly different?
Oh, for the flag one, I first classified, no, I changed the label for either 1 or 2 into a consistent label, like saying like I changed all the 2s to 1 or changed all the 1s to 2.
Oh.
And then just did absolute value
Okay.
classification. And then like I set up a parameter if you're lower than the midlines and you're either 1 or 2. And then that way it was actually biased against like to the part it's biased towards the direction of like which way you initialize it as. So I did it twice and stacked the predictions together and then got like a 90% accuracy.
Interesting. Okay, I'm going to read your code. So guys, some of you have sent me your notebooks. I apologize, I've been rather busy. Now 4th of July is coming and I'll be reading it over that. And I'll give you guys feedback on your notebooks.
Asif, one quick question on when you did random forest on river here, how many subset of features? One, like there are only 2 features here. So did you?
Yeah, that's right. So what happens is that in a situation like this, it will pick up 1 feature at a time. It will just build a tree of 1 feature.
And Asif, same question with a different part. So when we select like 1,000 decision trees for the random forest method, how those trees are different? Like when we have only 2 features.
Oh yeah, the reason is that even if 500 trees pick 1 feature and other 500 trees pick the other feature, remember they are being given different subsets of the data. Bootstrapping is happening, right? Okay. They're getting different parts of the data. That's where it is. So it was a very simple problem. It was there just to teach you guys the importance of feature engineering. It was just a didactic data set I created to bring out the importance of that.
So how do you prune the tree for decision tree and code?
Yes. So the pruning of the tree is built in here. Let's talk about it. The next example, which will be more complex next week, let's come to that. What you do is you force it to limit the depth. You say max depth is equal to, let's say, 4. Actually, in this problem itself, I'll do that. So you'll see it. You'll see it happen. Right. Just give me a minute, and you'll see this happen here also. Oh, what did I do? Okay. Where did I suddenly come here? Okay, guys. At this moment, are we done with the river and the flag? Is it looking simple? Like, are you feeling more comfortable with the solution, guys? Guys, I'm getting a lot of sound in the background. Are you? Yeah. Okay. So, any feedback, guys? Recording on pause for the time being. Pause. All right. So I'll go from the beginning once again quickly. So we're going to do the California data set. Much of it is familiar territory. The one new thing that I introduced is how to style a table, any table. These are CSS properties. The beautiful thing is that the pandas data frame has an integration with CSS styles. You can style the data set and it looks different. It looks pretty, I suppose, than the vanilla version without any styling. Well, my styling is not particularly pretty, but if you're really good at CSS, you can make this table, I suppose, even prettier.
Yeah, with all the cool colors.
Yes, you can do it with all sorts of cool colors. I put salmon here, but you can do some different colors.
Yeah, light blue or something.
Yes.
So
It's not a Jupyter specific command, right, Asif? I mean, is this like a HTML table that the Python is giving out with that command?
Exactly. So it is emitting out a HTML table that's emitting back.
Okay. Okay.
Yeah. See, one thing is there, Jupyter and Colab, Colab is based on Jupyter, are pretty much the de facto standards in data science, right? If you do, the one thing that you may graduate to is PyCharm, right? PyCharm has the support for notebooks, this style notebooks, Jupyter style notebooks. So all of them will respect this HTML output and so forth. They will all respect it. So now moving forward, one of the things you do is, this is a new thing I'm introducing you to. See, when you get data, guys, you don't know that data is clean. You should assume that real life data is not clean. This is a real life data. So a little bit of a background on the California housing data to repeat. See, in California, one of the perpetual obsessions, especially in Silicon Valley, are the house prices going up or down, right? Because most Americans, and certainly most people in California, their biggest asset or their principal, I mean, the value or retirement money is often stored in the house, right? It is the house itself. So as the market goes up and down, the individual people, they see their fortunes go up and down, right? And people worry if the house price is crashing. People get very excited if the house prices are going up, unless you're on the fence wanting to buy a house. If you want to buy a house, of course, you love a crash. But the moment you buy a house, you want the house prices to boom. So it's a real data set from the 1990s, I think 1990 data set of California. You see how the house prices were then. Now, 1990 is just 2025, I think it's 1990 or 1995, I forget. This data was gathered. And what looked like an expensive house then will look like I mean, for the same money today, you could probably buy yourself a shed or something like that. California houses, the prices have really gone up. So this is not a time series data, temporal flow. It is very specifically a snapshot in time data for California. What were the house prices then? This data set is available in Kaggle. I must have taken it. I'm guessing I took it from here. It is a data set that was published actually. And it is also mentioned in this book that I recommended you all to read. Okay? So it is the same in your textbook, the Python one. This is discussed. So you can go back and read a chapter there and see. And actually, I have not, I'm embarrassed to say that I haven't really looked at how he has done it. Perhaps he's done some things better. You can go and tell me about it. So, well, this is a command. What it does is it finds if data is missing in some of the rows and columns. It is real life. Whenever you gather practical data, you will find that some rows will not have all the values present. They will be missing values. It's the nature of it. So suppose you're taking the weather, your temperature, pressure, whatever it is, wind, and let's say that the guy is doing it manually. Just forget modern instruments for a moment. So you can easily imagine that if it is too rainy, the guy won't go out and take all the measurements. He'll just run back, or some measurements may be wrong. Somebody may delete it and so forth. So things like that. Sometimes you don't have all the data for all the rows, all the feature values for all the rows. So you need to inspect that first, unlike the river data set or flag data set, which were didactic data, and so there were no missing values. In real life data, you will get noise, you will get imperfections. So you need to acknowledge those imperfections and study it. First thing is, just as an exploratory data analysis, let's look up here. What are the columns we have? Longitude, latitude. It gives you the coordinates of a house. Right? Actually, it's not at the level of a house, but it's at the level of a city block. But it gives you the coordinates of a city block. House, excuse me, median age. As the name suggests, it gives you the median age of the houses in that block. So some house may be very recent, some may be older, but generally in a block in US, you know, most of us live in row homes, right? Cookie cutter homes. So quite often, almost the entire neighborhood sort of comes off the ground at about the same time. So median house price, median age is a measure of what the middle age is. Sometimes houses have a huge variation, new and old. Total number of rooms in the house, again, is a pretty good measure. It's worth looking at. Right? Now, it looks very odd. The total number of rooms is minimum is 2 and maximum seems to be a huge number. Why is this possible? Because it's not the number of rooms in a house, it's the number of rooms in a block. And if the block has a lot of apartments, high-rise apartments and so forth, tenement housing, you may have a lot of rooms. This is the total number of bedrooms available. Typically, a number of bedrooms is a pretty good estimate of the number of people living there. Right?
Yeah, you are right. You're right, because you see the number of households is also too many there.
That's right, yeah.
That's how you can figure out, yeah.
Right, households and yeah, so you can see that. And then you have the households, population, median income, like, you know, what is the median income of people living in that block? And the target variable is we want to use all this data to predict the value of a house. What would be the value, the selling price of or the estimated value of the house, median value in the whole block, city block. This ocean proximity is important. As you guys know, in California, it is pretty expensive to live on the beach. Right? We have a lot of coastline, but the coastlines tend to be more expensive than inland. And so ocean proximity matters. If you live on the island, for example, Catalina Island or somewhere, it could be quite expensive. It's worth looking at. So those are the features. Just looking at this value, can you tell which of them is a categorical?
Ocean proximity.
Right? So next thing you do, you look at the missing values. In missing values, if you see a white horizontal line, it means data is missing. So which of these features has some rows in which there is missing data, guys?
Bedrooms.
Bedrooms is one. And if there isn't something else, it's barely visible. Right? How many rows of data there are and so on and so forth, it's a measure. Then, so it turns out that there is a total bedroom and total bedrooms. That's the only thing where any data is missing, right? And if you have total bedrooms missing, then sometimes it affects all of these. That's about it. It doesn't mean much. Now, I taught you guys about this thing. What was it? About profile, the pandas profiling.
Yeah.
So you can use the pandas profiling. Good thing with pandas profiling is some of the things that I did by hand, for example, missing value analysis, in an abbreviated form, it does it. So when you look through this, pandas profiling is pretty good. It established that most of these are real valued, but it was smart enough to indicate that ocean proximity is categorical and there are 5 values. What are these? You are less than an hour from the ocean, you're inland, you're near the ocean, near the bay, or you're in an island. So there are 5 homes or 5 rows of blocks that seem to be on an island. So which is the island in California?
Alcatraz.
Alcatraz is one, certainly. Yes.
But I don't think anyone, I don't know if anyone lives there.
Catalina?
Catalina, exactly.
Yeah.
The islands. Right. So then you can look at the interaction. For example, how does longitude and median income, latitude and median income vary, right? Clearly you notice that latitude and median.
Hey, Asif, can you please quickly recollect interaction? Is that collinearity?
No, it just is showing you some sort of a correlation between.
Correlation only, okay, that's correlation.
Yeah.
Because there is correlation below, so I'm not.
That's right. So from this, it may not be very obvious, but you can see that San Francisco Bay Area is filled with people, with a certain income value, and then there are people in Los Angeles who have that income. If you go longitudinal, right, you see that also. It's a little harder to see longitude-wise, but at certain longitudes are the most, hang on, median income here, longitude and median income. Again, you see this value that Bay Area, so the two big income areas are Bay Area and Los Angeles. You can sort of see that. This is the correlation. You can see correlations are there. Very prettily, it draws out the correlations. Right, and if you want to understand what these different correlations are, you remember that I taught you guys Pearson correlation. All you have to do is toggle this and it will explain to you, right, what these correlations are, Kendall Tower and so forth. If you want me to explain it, I'll be happy anytime to do it on Saturday. Ask me. But today I want to move a little bit faster. So you can see that it gives you some sort of a missing value analysis. Pretty much it says that none of the rows are missing, except for, well, why did it not show total bedrooms either? Well, this does not look right. Okay. It gives you a few sample rows, last row, this is it. Then let us, so now I want to introduce you to some techniques. One of the things is when you get geospatial data, it's always a pleasure to visualize the data, right? And to visualize the data is actually very easy. Do you notice what do I do? This, let's go through this code. I got the minimum and maximum longitude of the latitude of the longitudes, minimum and maximum latitudes. Using this, what can I do? I can find the center of the map, isn't it?
Yeah.
Yeah. Does this line, these three lines make sense? It's very simple. All I'm trying to do is the center. So what I will do now is I will create a map, and Folium is an excellent library to create maps. You see, in one line, I'm creating a map. I'm just giving it the central location, longitude, latitude, and I'm giving it the zoom level. You can start out with the zoom level. Of course, you can zoom out. So if you notice that with my mouse, I'm zooming out. Right? This is interactive map. These are live maps. It's a pleasure to actually be able to create it. You realize that with just a line of code, we are able to create it. One line, right? And on that map, which will be an empty map, now I need to project our points. Each of these points, I projected it. Our data points, I projected it. Longitude.
That color has to be like in hex code?
No, you can put whatever color you want.
Okay.
You can put red, blue, green, whatever.
Okay.
I must have been fooling around with something. I like this color. Right. Though these days with coronavirus, this color is a dangerous color, right? Means danger. Things are not going well. Anyway, so this is it, guys. So do you see how nice it is? How quickly you can create maps in data science. So, you know, these are all the tools of data science people use. It is good to know how to make maps if you have geospatial data, right? But you don't need to make maps. You can just draw a simple scatter plot. If you just did a scatter plot of the data, you would realize that you would get exactly the same thing as if I just made the scatter plot of points. And let's look at the scatter plot. I'm making a scatter plot. X and Y are the latitude, longitude. I'm coloring it based on the median house value, which means that if the value of the house is high, it will be more red. If the value of the house is low, it will be yellow. So yellow, orange, red. Color maps are, again, let me remind you what color maps are. Whenever you create scatter plots or plots in your code, you have to be careful of multiple aspects. One is the aesthetics. Together they should look pretty, right? They shouldn't be jarring to the eye. The second is disability. You know, a lot of people are colorblind. So people have sat down and they have created this color map of good color, the color ranges, which fulfill both the needs.
Contrast, yeah.
There are enough contrast, they have and the color blindness sensitive. At the same time, they give you the aesthetics and the beauty. So this is nothing but a scatter map, a scatter plot. And then the size of each point is how much population there is. And the color is how expensive the house is. So if you look at this map, can you see, guys, that places, so deep red is expensive places, they also tend to be high population centers, isn't it? Which makes sense. Cities are densely populated and the median home values is very high there. Is it making sense, guys? We all know about homes, we all know cities, so it makes sense. Can you tell where is San Francisco and where is Los Angeles in this?
San Francisco, 38 minus 122.
Yeah, that's right. You can literally see, this is not a map, this is just a scatter plot of data. And yet you can see a lot here. You can see the San Francisco area. You can see a little bit of the Santa Barbara area. You can see the Los Angeles area here and the San Diego area. Not only that, you can also see Interstate 5 run through it. Do you see it, guys, effectively? This line here? Those of you who have been, now let's correlate it to the map and see whether we are right. So look here, guys. Do you see this?
Yeah.
Right? All the cities are along this. Right? And actually it's not, I don't know if it is Interstate 5, I think it is. Yeah, but yeah, there you go. I think there's also a California route that goes through this, that may be more through the cities. I think Interstate 5 tries to avoid the cities.
You can overlay the map on the scatter plot, right?
Yeah, you can do that, and you can do. So anyway, I gave you at this moment, I was just trying to give simple code. So you see, this is your standard scatter plot. I've just prettified it a little bit.
Yeah, see, on the right-hand side, that 100,000 to 100,000, that is basically your C.
Median house value.
C, right? Okay.
Yeah. So in those days, in 1990, perhaps, 500,000 used to be the cost of houses, very, very expensive homes in Los Angeles and San Francisco. Today, what do you think 500,000 will buy you? Those areas.
You have to go to Tracy.
Yes, that's right. And then you need to literally add a zero there. It's close to 5 million.
Yeah.
In those places. I was just looking at the house prices in Atherton. I think they all are 6-7 million and so forth. So, by the way, any rich participant here who lives in Atherton or something like that? So, all right. So I put this side by side now, guys. You can literally see the scatter plot in this map. They look so close to each other, isn't it? Now, the other one thing I realized that the ocean proximity is a categorical variable. So I'm explicitly changing it to categorical, right? Instead of a string. It's just a good practice to do that. Any surprises so far, guys? Anything that needs explanation? Does this statement look very easy? These two things, by now, is it looking very straightforward and easy, guys? It is a categorical, so I'm making it a categorical.
Yeah.
Yeah. Then this is the describe. By now, you must be familiar with it. We are describing it. Then what do? I draw histograms of each of the variables. When I draw the histograms, can I just shrink the font size a little bit? So I want to see the histogram in one single shot. Yeah. So what is the histogram? In histogram, you can choose the number of bins. What does alpha 0.4 mean, guys? Who would like to enlighten me? What does the alpha stand for?
Is it like how transparent it is?
Exactly.
Transparency.
It is the transparency level. How saturated it is. Alpha 1 means completely saturated, opaque. Alpha of 0 means completely transparent, invisible. So 0.4, why did I do that, by the way, guys? Why did I not have it? If I don't put alpha, what will happen?
1.
Yeah, these will be very saturated colors. A bit of pastel color adds aesthetics.
Yeah, hurts the eyes also.
Then, now, why did I do this? X rotation is 90 degrees. Why did I do that? Can you tell me what it is doing?
X-axis is, like the numbers are rotated 90 degrees, so you can read it well.
Yeah.
Uh,
And if you don't do that,
Otherwise, it will overlap.
yeah, otherwise they will. Exactly. Great. And figure size 2020 means I'm giving it a rectangular shape. Right? Just enough big. You can decide what your figure size is. 2020 here was good. Maybe I could have made it a little bit bigger. Now, the pairs plot is interesting. This is again, those of you who did ML100 with me know what pair plots is. It is nothing but the scatter plot of two variables taken at a time. So the way to read it is a little more complicated. Let's take this. What is the relationship of longitude to population? Do you notice that there are two humps here? Can you explain why there are two humps? Why is this peaked at two places?
San Francisco and
California and San Francisco.
Exactly, absolutely. San Francisco and the
LA.
area and the LA area. So
Yeah, the bimodal.
bimodal distribution. California is bimodal in most of the things. So it's quite interesting that most people of California live in these two cities, and the rest of California is empty. People often say California is very expensive, very expensive. Actually, if you go away from these two population centers, California home prices can be quite reasonable.
Yeah.
Yes. So in case you have an urge to run away to the middle of nowhere, or maybe in the middle of Arizona or something, remember, you don't need to run that far.
Yeah. There might be, people might do that if this trend continues like this, people might even do that.
Yes. So you can see once again near the sea, how often are people, this is a box, this is called a category plot. Given latitudes, how much of values there are. Once again, you see that there people are sort of distributed all along. Inland, at certain inland, people are at all sorts of latitudes. Near the ocean, people are at, they're closer to this latitude, the 35-degree latitude, which is closer, most likely to San Francisco area. I mean, the Los Angeles area. Near the bay is, of course, all San Francisco population, and so forth. It's just a dish. So these are the plots, guys, I'm introducing you to, in case you are not introduced to that. What I would say is, as you study this notebook, and those of you who did ML100, of course, have gone through this exercise at a more leisurely pace, but those of you who have joined ML200 directly, these are the landmark or the stereotypical or ubiquitous plots that you make in exploratory data analysis. So become familiar with the syntax. In the beginning, it will all feel rather magical that you're invoking some magic mantra or some obscure shlokas and something is happening. But gradually, this will all become very real. It will begin to look very easy after some time. It is just standard Python code. If you want, I can explain any one of these code to you. Like for example here, do you agree that this one line is self-explanatory? It is saying go make histogram, do bins of 50. What does the bins is equal to 50 mean?
50 buckets.
Exactly, 50. So when you make histogram of a numerical variable, you have to put values into bins because you're counting how many values fall in each bin. You take 50 bins, alpha is this we already talked about, figure size we talked about. So there's no magic to any one of these. Likewise, the pair plot. This is a bit more going on here, but still it's 4-line. I'll explain it to you. You make pair plots between this, alpha, size is 80, all of those are self-explanatory. Then you say that along the diagonal, make the histograms. Okay, do you see? So these histograms are the same as the histograms here. Then the next thing it says is that what is the color in the histogram that I gave? Hue is the ocean proximity, how far you are from the ocean. That's the coloration. Then in the upper diagonal, on the upper side of the diagonal, the pairs should be scatter plot. And in the lower part, there should be something called kernel density estimators. Those are sort of, think of it as some, at this moment, KDs will deal with them much better, but think of them as, these are well probability density sort of thing, but think of them as some sort of a heat map at this moment. Right? A very rough idea would be heat map, but we'll talk about this and learn about this in more detail when we do the workshop, the boot camps.
Are those in the heap? Are those numbers like table of numbers?
In between, no. These are just the legends. This picture is very dense. See, the thing is,
Okay.
we made this picture of size, this size. When you have so many variables, you want to blow up the size of the picture so that everything is well separated and you can see everything. Right? So you would make this picture to be more like 100 by 100 and put it on the wall.
Yeah.
Then all the things will show up properly. But it also shows what happens when you have too many variables, right? That you cannot put everything in a single visualization. This is already beginning to push the limits, isn't it?
Yeah.
Imagine that there were 30 variables. Then the pair plot would be horrendous. So what you do is you make it in pieces, or you pick a few important ones and you make the pair plots.
And there is nothing like you have to see all of them in one place, right? I mean, you could, when you're analyzing, going deeper, you can always go one by one, right? So it's okay.
One by one and make scatter plots. Absolutely.
Yeah.
You can do that. And now these are called beautiful. If they look pretty, these are called Violin plots. They literally give you the box plots, but Violin's a little bit prettier than box plots. They give you counts like median household age, how many homes, and this is why, remember that ocean proximity is the categorical, right? So based on the color, so there's value. So this household median age, you can pretty much see that the median age this is the ocean. Catalina is pretty old homes are there. You don't have new homes. Most likely, they don't allow new homes to be built. It's an island. They must have very strict regulations. Right? So this is it. And the same data, I just show you that you can do it as a regular box plot. See, with all of these things, and when you present data, guys, people underestimate the value of clean visualizations. Visualizations, if you clean it up, it sort of creates a bit of aesthetics. I haven't done much. You can do much better than this. But for what it is, now all of these things that I'm doing, box plot, category plot, Violin plot, none of them are hard. These are all features there. You have to just go use it. You have to know that those things exist and you have to go use it, right? A count plot, how many homes are there? So most homes, it turns out, are less than 1 hour from the ocean in California, which makes sense. California is a long and narrow state. Most homes are inland. There are some, this is probably the Central Valley. Maybe there are, but not that many. Then near the bay, near the ocean, this is it. Right? Now, correlation, you realize that any two variables could be correlated. It shows you the degree of correlation. Now, we already saw that in profiling, in the pandas profile. So I won't go more into that. This is the, oh, by the way, here I wanted to show you something. Quite often, when you write documents, you want to write it in LaTeX. People often ask, how do I put the output into a research paper that I'm writing, something. So it's very easy. Any data frame in pandas, all you have to do is do LaTeX. Now, those of you who know what LaTeX is would find this magic mantra very easy to read. If you don't know LaTeX, don't worry about it. LaTeX is a language in which in the mathematical communities, computer science and math and physics, etc., most papers are published. Okay? So this is the syntax for that. Now the same correlations, we show it as a heat map here. Worth looking what the high correlated are. So I'll let you ponder over it. Median age is highly correlated, negatively correlated with, let us say, with many things, total number of rooms. Does that make sense, guys? Median age is negatively correlated with total number of rooms and total number of bedrooms. What does it say?
new houses are smaller?
No, the opposite. The bigger the house, the older the house, the smaller, the lesser the number of rooms.
Yeah, yeah. Actually, if you go to the older house, you will see the bedrooms were much larger.
Right.
So
And
the number of bedrooms were small as a result. Yeah. But these days, if you go to the houses, you will see bedrooms are very,
yeah,
I mean, they like to, because the price is based on number of bedrooms.
right.
So they increase the number of bedrooms. Yeah.
Increase the number of bedrooms and tinier bedrooms. Okay, guys. So that was it. So now let's come to regression. I taught you guys decision tree and the random forest. Let's see if we can do that. Very simple. If you read the river data set, you'll find this easy to understand. So we need to do some data pre-processing. First pre-processing we need to do is that we need to do one-hot encoding of the data. What does that mean? One of the predictors was ocean proximity. It's a categorical variable, right? So we need to convert it into a numerical variable. And the way you do that is you take all its values. So for example, are you within 1 hour of the ocean? Yes, no. Are you within proximity? Are you inland? Yes, no, right? Are you, so on and so forth. Are you on an island? Yes, no. Are you near the bay? Yes, no. Are you near the ocean? Yes, no. So what have you done? You have burst out all of these into this different columns, right? Different features. This is called one-hot encoding. So you can do one-hot encoding of the data. Once you do that, the other thing that I'm doing is I'm dropping all the rows that don't exist. Is that a good practice? Actually, you have the luxury to delete or drop rows that are defective only when you have a lot of data. Here we have a lot of data, 20,000 rows are there, like 20,000+ rows are there. But if the data is sparse, you don't do that. You do something called imputation. You try to fill in those values and keep those rows and use them anyway, right? It's like when your car has a nail in the tire. There are only two things you can do. If you're rich, you go and change the tire immediately. Well, if you're like you and me, then I suppose you'll want to take the nail out. Unless the tire is old, you would like to have it patched. Right? So it's like that. Each of your row of data, you would like to patch it up by imputing some value, filling in those gaps with some value. The imputation is the topic. Usually these little things or practices we do in the boot camp, we don't. So, but here we just delete it. Gradually, as we make progress, I'll teach you guys imputation. Then we impute it. Now, notice one thing, guys. This data, do you see skew in the data? Is the data symmetric, or you see a lot of skew in the data, guys?
Skew is there.
Skewed.
Yeah, the data has a lot of skew there. One more thing you notice that this particular thing, household median age 50, right? 50+. At 50, they have sort of clubbed all data that are 50 or plus into 50+ category, bin. So you have to watch out. It will screw your analysis, and you'll see how it screws your analysis after a little bit. I leave this as an exercise for you to deal with this part. One way you can do it is not take the data 50+, right? Take it out and so forth, but we'll deal with it. This data is skewed. Is it right skewed or left skewed? Remember the trick, guys. If you think of it as the beak of a duck.
Right skewed.
Right skew.
Yeah, the beak is looking this way, right? The duck is looking this way. So it is right skewed. All of these are right skewed. Some of them are very strongly right skewed, right? And median house value, the target variable, also seems to be right skewed. What can you do about it, guys? How can I take care of this skew? Well, you could do the whole power transform and find the right transformation to normalize it. But a cheap way is just take the log of these, this one and this one and this one and this one. Whatever you think needs a thing, you can do as a pre-processing. You can take a log. If you take a log, it's a trick. And again, I'm talking about things that at one point I've taught in depth to you guys. But suppose I take the log of it, that is the log transform. By the way, this whole thing, most people don't pay attention to, and you will see what happens. If you don't do this, your R squared value will be about 6 to 10% less. Right? But if you're careful and you do this, and I invite you to do this, guys, comment out this code, run the analysis, see what your model metrics are, performance is, and then do this and see your model performance. It is quite interesting actually that most of the notebooks that I saw of California dataset, which have been posted in Kaggle and other places, they did not do this transformations. Yeah? If you are using, it is always good to do that feature extraction or data preparation carefully. When you do it, you get the extra bit of accuracy, the extra bit of performance, not actually, extra bit of performance. Right? You will get. So now when you do the transformation, do these things look much more normal, guys? Are they better? Right? The skew is gone, right? So now that it is gone, what have I done so far? I have massaged, pre-processed the data, data pre-processing. After the data pre-processing, then I go and, so what were the things that I did in the pre-processing? I did, let us summarize what all things I did. I mention it here, convert the categorical to one-hot encoding, drop the missing values, extract the feature space and the target XY, right? All three things. Then finally, I also do the log transform because I looked at that. So this is the value of drawing those histograms, guys. They're not just one thing you do as a ritual. You use it to make some decisions about data. And once you do that, you now take this and use, does this look totally easy to understand, guys? What am I doing?
Oh, this is
Doing training and test.
test split.
Okay. And then I'm going to try a slew of models on it. First, I'll do a simple linear regression. Right? When you do a simple linear regression, do you remember this lines of code, guys? This is straight from your river data set. Right?
Yeah.
You just the linear regression fit it. Now you notice that things are beginning to fall into a repetitive pattern here. It's more about thinking the code begins to look very easy and familiar. It's exactly the same code. When I run this code, I get a mean squared error, which is fairly low actually. And I get a coefficient of determination, which is 69%. 69% R square for this data is actually, I would consider fairly impressive. If you had removed the outliers, it would become even better. I leave that as an exercise for you. So one basic thing is that outliers, there's not enough data, not enough information to make a judgment call for them. So you could do one thing, you can remove the outliers and say, I'll make a separate model for outliers, something else, and let me make a better model for the inliners, inline data that is not outliers. Let me leave that as an exercise for you guys. Huh?
So Asif, where do I see that outlier information in the graph?
Oh, it is all here. See, if I look at this graph here, look at the histogram. Do you notice that all these outliers are there in the box, whiskers plot, right? So anything beyond the whiskers, do you see this is the box, these are the whiskers. Anything beyond the whiskers are outliers. So latitude has outliers, well, that's not harmful, but total number of rooms has huge outliers, right? Do you see that? The main box plot is here, and then there is a long tail of outliers, total number of rooms, total number of bedrooms, population, they have outliers. The households have outliers. And let us also go, and income has outliers, right? So let us go and verify whether that shows up in the original plot. Do you notice that this tails off, but it goes to 6,000. Why does this box plot, why does this histogram go all the way to 6,000? We can't see it, but there must be some 1 or 2 outlier values here, isn't it? In all of these, there are some outlier values sitting here. Like for example, total number of rooms, 15, right? Hang on, households. Let's look at the household, right? In some city block, there are massive number of households. In certain median income, Some people seem to have a fairly high median income, even after, pretty high median income. I'm assuming that this is in thousands or something like that, but whatever it is, look at the population. It goes all the way up to here. Some blocks are really heavily populated. So the data is filled with outliers. Do you see that? Guys, do you see that? It is a clue. Like, you ask yourself, why is this histogram going all the way till here? It means that there is data that I don't see. So if you chop off the outliers, guys, your analysis will become better. And I leave that as an exercise for you. It's also one of the things people forget to do, actually. In fact, I was just in the break, I was looking at the California housing, and I was looking at some of the notebooks and what people have done, even the more celebrated notebooks, the kernels that people have done. By the way, you can learn. I highly encourage you to go and read some of the highly voted kernels that people have created and see what things they did that you've missed, because you can learn from it. At the same time, you can take pride that you did something more carefully that a lot of them missed. So this is the way for you to get a reference of how good you are yet. These people certainly think they have done a great job, which is why they have posted their notebooks here. Right. So go check it out, guys. You'll be pleasantly surprised that by the time this workshop ends, you would realize that your notebooks look better than most of the notebooks there at Kaggle. Anil, do you agree?
Yes.
Yeah. Begins to get better and so forth. All right, so we are making a linear regression model, and we achieve an R square of about 70%, or 69 points, let's say, give or take. At this moment, guys, remember what did I teach you in ML100? It is not enough to know that you're getting a decent R squared or a decent mean squared error. What you need to do is what? You need to be able to do a residual analysis and see all is well. So you begin to see that this is your residual analysis. When you look at it, first thing you notice on this side, do the errors have a bell shape? Do the residuals have a bell shape?
Yes.
Yes, they do.
Yes.
Yeah. Here, there is a little bit of a pattern here. By the way, ignore this. This is coming from the limitations in the data itself. Because remember, there was a hard cutoff in the data in one of the fields. This way, this is coming from. You can ignore that. But it is mostly there is mostly a sense of homoscedasticity, except for these outliers are screwing it up. They seem to be there more prominent in the lower predicted values than in the high predicted values. So if you remove the outliers, it would get better. So it is not perfect, but it is pretty good. After all, we are using a linear model for a very complex data set. What is the relationship between prediction and reality, guys? This is the relationship between prediction and reality. Does it make sense? Is it a positive or negative correlation?
Positive.
Positively correlated, isn't it? Why? Prediction and reality are positively correlated. They're along the principal diagonal. So you can see the deviation. See, a perfection would be if they were along this a gray dotted line, and they are along this dotted line. Well, not quite perfection, but pretty good. Right? If you're searching for points that can be of high leverage, high influence, it gives you a sense of high influence points. Nothing pathological. All looks good. Now, this was your linear model, guys. Do you notice that just a good application of a linear model took you this far? By the way, if you had not done all of those log transformations, etc., your numbers would not be so good. Huh? They would be much worse with a linear model. Try that out. So 69.1. Now you ask yourself, if I had regularized the data, would I get a better answer? It turns out regularization does what? It suppresses overfitting. I haven't, obviously I apologize for those of you who have just joined. Overfitting means, the data has high variance, overfitting. There is a method to suppress it. And you suppress it by different degrees of suppression and see which one is the best. and then you, whichever is the best, you use it. It has gone to 69.12. Well, 69.11 versus 69.12, pretty much the same. If you look at the coefficients of the model, let's look at the first three coefficients. 0.165, 0.164, do they sort of match the previous one? 0.165, 164, then 003 and 19, minus 19. So 003 minus, so you realize that the coefficients are almost all the same. It means that the data does not have, your linear model does not have overfitting, right? And it sort of makes sense. Linear models like tend to have underfitting problems, not generally overfitting problems, right? So, well, that is what it is. If I had made it a polynomial model, so I leave this as an exercise, guys. See, somewhere I taught you polynomial regression. See if you can extend this and make it a polynomial model. Be ready that it will be a big computation, because even if you go to quadratic form, 11 square is close to 110 combinations, right? So you will have an explosion in the number of variables that will show up. Try it out, see whether it gives you anything. But when you do a polynomial, you must use ridge regression or lasso, whatever it is, to suppress that. Better is actually use elastic net. It's a combination of both. Can I leave that as an exercise, a homework for you guys to try? Please do that. Huh? Then we talk about decision trees now, because we learned decision trees the previous week and random forest this week. Let's look at the code for decision trees. Guys, I trust by now this code looks obvious. I build a regressor, I give it the data to fit, and then I use the data to predict the labels. So far, so good, guys?
Yeah.
Right? These are your predictions. Labels are your predictions. So people use y hat or labels, whatever you like. Huh? Labels is more typically for classifiers. I tend to use y hat. I don't know here. I wasn't being too careful, so I just use the word labels. Any variable name. So there we go. And what is the R square I get from a decision tree? 67.72. Is it better or worse than linear regression?
Worse.
Worse, actually. And look at the complexity of the model this tree built. So it is an illustration of what principle? Something about lunch that I keep talking about. Anybody can remind me, what do I say?
Free
No, free lunch.
Yeah, there are no free lunches.
NFL, right? Yeah.
Exactly, it's an NFL theorem. That no one algorithm is, in quotes, powerful, more powerful. Every algorithm has a place under the sun. Sometimes one works better, sometimes others. So don't let anybody tell you that decision trees are more powerful than linear regression or something. Linear regression is too basic. It was a point worth emphasizing, so I'm mentioning it to you. You can visualize this. By the way, this is hopeless. The built-in visualization from Python, this scikit-learn, is not terribly illustrative. For visualization of graphs and trees, GraphViz is the best. If you use that, and I can show you what that becomes. Let me see what that becomes. California. California. Housing. Okay. Oh, I think I removed the old directory. Okay. We won't worry about it. There was a PDF version, a prettier version that I could show of this. I don't want to run this now. It will take a bit of time. This is if I use yellow brick, the same thing, do I now see a pattern? Does this look much worse than the linear regression plot, guys?
Yeah.
It does, right? It doesn't look as nice as this. It is actually a little bit worse. Right? But good news is that I still have a more or less normal distribution of errors. Here, you can see that this line is a little bit more off the diagonal than the previous one. So let's try our luck with an ensemble method now. Remember, I told you that ensemble methods can be more powerful. Let's try random forest. Forest is just made up of trees. Again, took 1,000 trees, 20, well, parallelization is 20. It executed in 5.79 seconds. 20 is something you guys can probably run on your laptops if you have multi-core. I typically run it with 100. It runs faster, but it doesn't matter. So here we go. You go and do the predict. Again, by now this code, guys, I hope it's beginning to look very easy. Do you notice that between the decision tree regressor or linear regressor, all I had to do is change this word, the algorithm name. It has become random forest regression. I apply it, get the labels, get the predictions, and what do I get? I get an R square of 83.6. Yeah. Is it better than linear or worse than linear?
Better than both.
Better than both, isn't it? That was 69 and about 70%, and this is close to 84%. So for this problem, random forest is certainly the best of the three algorithms that we have tried. Isn't it, guys? Right? Now, this is what people tend to miss. They tend not to do the residual plot. But if you look at it, isn't the residual also looking much better now here?
Yeah.
There's far more
pattern.
Elasticity. The residuals do have a normal shape, normal Gaussian distribution, much better. So here, obviously, the random forest is the winner. Remember that in the river dataset, the careful hand-generated feature extractions were the winner. Here, there are too many variables, and it's harder to do feature extraction. But there are feature extractions you can think of. So let me tell you. And by the way, one of the Kaggle notebooks did it brilliantly. Some fellow has done it. He said that one good feature would be, or she said, that one good feature would be the distance to the metropolis, nearest metropolis. So distance to Bay Area or distance to Los Angeles, whichever is smaller. And he made that a predictor, and he came up with a beautiful visualization. Look up, his notebook will be there. Classic. I wish I could have found and opened and showed it to you. I'll leave this as an exercise for you to find out. So you can do a lot of further feature extractions, right? You can and make it out. And the other thing you can do is join this data with other data. For example, you can join it with educational level, add at any given latitude and longitude or city block, what is the educational level? You would realize that educational level has a huge influence on the home prices. Birds of a feather flock together, right? So you can go on creating more and more features by joining this data with other data sets. And that is where the magic is. Most of the time, if you're given data, you get more data, not by getting more rows of data, but by getting more features into your data set somehow. You manufacture features, or you take data that is not there by taking, Bureau of Labor Statistics data or something like that, economics data, weather data, something or the other, and you bring it in and see how
School rating.
Go ahead, Vijay.
No, I was just saying school rating.
School rating, yes, excellent. School rating is a huge determinant.
Yeah, so we can get like the zip code, and then based on the zip code, we can get the school.
Yeah, exactly. We can get the overall school rating, right? In California, the schools are failing, so it's like almost an arms race. Whichever few school districts are good, everybody wants to go there, and the house price just skyrockets. In my own case, I have an illustration. I have a house which is much more modern, bigger, nicer in Vallejo Hills. And I have a house here in Fremont, as you know. Right? Proximity matters, but also the fact that the school district in Fremont is superior means the house price is practically 3 times over for a much worse house, actually, much older house.
Yeah.
So it's an illustration of that. So anyway, when you visualize, so one of the things I did is, a forest is made up of trees. So you might be curious, let me look into one of the trees. So here it is, inside the forest, there are lots of trees. They're called estimator underscore. So member variables are always hidden with an underscore. Now there's a convention. The output variables have an underscore here at the end. And in Skikitlan. So I just took the first tree. No reason why I should take the first tree. Could take any one tree. But do you see how complicated it looks, guys? Do you think there is any interpretability here? There isn't.
So Asif, what is it exactly showing? So one tree means what is it exactly showing here?
Oh, look at this. There is this root node splitting into two nodes, splitting into two.
Oh, okay. Oh, they have shown the trees like, okay, now I get it. Okay.
Yeah. It is practically indecipherable.
Oh, okay.
So that's how it is.
So
And
some pruning is needed.
yes. So one of the things I introduce you to today is a very rough measure. You may say, all right, what factors are really important? Which factor is more important than other in determining a house price? This is in 1990s. Let's see if the results agree with our intuition. Feature importance. Now, by the way, remember guys, that this is a very rough and ready measure, right? Usually feature importance is more local phenomena. In certain regions of the feature space, certain factors may be more important, which is why this feature importance, which people tout as a big virtue of decision trees and random forest, obviously it's worth knowing, and I'm explaining it to you, but don't take it with a huge grain of salt. Remember that it's a very rough approximation. There are better means of feature importance and explainability, and those are the Shapley values, and making local approximate models and so on and so forth. We'll come to that line. In the bootcamp, of course, those of you attended, you know that we covered a whole day to that. For Shapley, and by the way, those are non-trivial things. Shapley got the Nobel Prize in economics for one statement, effectively, one big statement. How much value to attribute to a player in a team. If you think of each of these features as player in the team that is together getting a sort of a home value, high home value, or whatever, then how much credit should go to each feature, that is Shapley value. We'll talk about all of those, of course, in the boot camp, or maybe next time. See, this by now you must have realized that this is a lot to digest. Are you guys feeling that we had a long?
Yeah. It was very overwhelming today.
Yes. So I don't want to bring in even more. So I'll leave it at the feature value. So
at least for me, I don't know about others.
So yeah, so let's keep it to that and see, does it make sense? So the biggest determiner of home value seems to be the median income of people living there, right? Well, that doesn't seem to be very useful, because obviously expensive homes can be afforded by rich people, isn't it? The home, like our income determines the house we buy, right? The banks will tell you that you can't spend more than 30% of your income as mortgage payments. It's the upper bound, right? It's a healthy bound. After that, you get into dangerous territory. So obviously you expect a median income to be very crucially related to the target variable, which is the home value. It determines the home you can afford. The second is, and so people if a house is priced at 1 million, you can ask yourself, what is the mortgage on 1 million, right? And let us say these days interest rate is what, 4%, right? So 40,000, that comes to about $3,200 a month. $3,200 a month means your income has to be 100,000. Or 100,000 plus, 120,000 roughly speaking, for it to be 30% of your, 40, right? 40 times 3 is 120. So your income better be 120 to 135 for you to be able to afford that $1 million house, minimum, isn't it? Do you see, guys, how the computation goes? So this sort of makes sense. I don't know, maybe, by the way, is my explanation right? I made a very rough and ready over the top of my head computation, hopefully. Okay, that's that. So the second is ocean proximity inland. Are you inland or not? We know that that is true. The more inland you are, the less the house price. Would you agree that that's true for California, guys? Broadly. Then the next factor seems to be latitude. Very true. What does latitude and longitude speak about? whether you're in the metropolis or not, Bay Area or LA area or not. Isn't it, guys?
Yeah.
Right? Location matters. Yeah? And anybody doing real estate will tell you. So what do these things? See, median income is more of a chicken and egg situation. Expensive homes are afforded by people who can afford them. So I would sort of discount that. But if you look at these three values, ocean proximity, latitude, longitude, what are they saying? They're speaking to the truism that any real estate agent will tell you. So they have a saying, a cliche, they say that there are only three factors that matter in a house for a house price. It's location, location,
Location and location. Yeah.
right? So those are all the three factors. And you see that said in so many ways out here. Oh goodness, there is a call. So guys, I need to go attend a meeting now. So I will stop here. This is the last one. The other factors are there, so on and so forth. Median age of the house matters, population, number of rooms matters, and so on and so forth.